Now let us discuss your electric field. For any charged body, may it be a positive charge or a negative charge, this charged body produces an electric field in the space surrounding it. And how do we know that indeed the charged body produces an electric field around it? So one way is if we have a test charge, let's say your test charge is Q naught, and we're going to use this test charge to test out if there is an electric field present around the space. Say for example around here, we have here a charged body, a positively charged body, continuous positive charge distribution, and we will know that if we can just erase this plus signs here and you just have this metal ball, you will know that this metal ball is producing, or you will know that this metal ball is positively charged if you say put some test charge around here, and then you'll see that this test charge will be pushed or will experience a force which is trying to repel this test charge away from your metal ball. And from that you can say that indeed, or you can say that this metal ball produces some electric field, and thus this metal ball is positively charged. Okay, in our study, or better ways, you can also replace this one by a negative test charge, and if this negative test charge experiences a force which is an attractive force towards the metal ball, you know that this metal ball is positively charged and produces an electric field around this negative charge. Now if we try to remove this one, this test charge Q naught, and label its former position as P, and then replace it with some point, just an ordinary point. Okay, now since we know that from our previous experiment that indeed there is some electric field around this metal ball here for your body A, the body A sets up electric field also at point P. So at point P here, you can calculate the electric field, which is the force per unit charge exerted by your body A on the test charge at P. Okay. From the previous definition of your electric field, you see that the electric force in a charged body is actually exerted by the electric field created by other bodies. From that, you see that you cannot experience, or you cannot have an electric force without the electric field created by other charged bodies. Force is a vector quantity, therefore your electric field is also 1. And we define electric field at a point as the electric force F naught experienced by a test charge Q naught at that point divided by the charge Q naught. That is, your electric field mathematically is defined as your vector E is equal to your F naught over Q naught. This is the definition of electric field as electric force per unit charge. The SI unit of your electric field is in Newton per coulomb. As you can see, your force is in newtons, and then your charge Q is in coulombs. So you have your electric field is equal. Your electric field has an SI unit of Newton per coulomb. From here also, you can see that you can calculate the force, okay, on a test charge Q naught by just your F is equal to your Q naught E. So again, this is the force exerted in a point charge Q naught by an electric field E. Some terms which we're going to use in the next part of this lessons. You have here your source point. When we say the source point, this is the location of the charge which creates the electric field. So it's called the source point. The field point, this is the point P where we are determining the field. So anywhere around your source point where you put your test charge or test point, that is what we call your field point. So you have your source point, the source of your electric field, and then the field point, the point where you are determining the electric field. Your unit vector R hat, we have defined this earlier. This is the point, or this points along the line from the source point to the field point. So in this case here, your unit vector r hat, which is equal to your vector r over the magnitude of r, is pointing from your source point towards your field point. So let's say, for example, around here, you have your charge Q, okay, which creates the electric field. So this is the source point, and then around here you have your test charge. This is your field point. Now, if you're going to define the unit vector r hat, your unit vector points from this one here, from your source point towards your field point. So it's not the other way around. So again, your unit vector, it always points from your source point towards your field point. Now, if you have an isolated positive point, okay, positive point charge Q, the electric field points directly away from the charge in the same direction as your r hat. So your electric field points outward, radially outward. Your unit vector r hat also points radially outward. For your isolated negative test charge, so the only thing that is the same here with the positive test charge is that your r hat. So your r hat will always point from your field point towards your source point. But here, since you have an isolated negative point charge, your electric field here points radially inward or directly towards the charge in the opposite direction from your r hat. So again, for your positive test charge, you have radially outward electric field. Your unit vector r hat points from the field towards the source. For a negative test charge, you have your electric field, which is radially inward towards the negative charge, but still your r hat still points from your field point towards your it points from your source point towards your field point. If we place a small tester Q nut at the field point P at the distance r from the source point, you know again that the force F naught is just your 1/4 pi epsilon naught, and then you have here the product of the magnitude of your charges. You have your Q times Q naught. Your Q naught again is your test charge, and then you have your r squared. And from that, so earlier we have defined that your electric field E is equal to your F naught over Q naught. If this one here is your force on a test charge Q naught at field point P, then the electric field is just this quantity divided by Q naught. Sorry. So it's just again this quantity divided by your Q naught. So Q naught just goes out, and you have here your electric field. So your electric field is just your 1/4 pi epsilon naught times Q over r squared. So what you have here, you just have your Q. So this is your source charge. So just a single source charge here. And in vector form, you have your electric field written as your vector E is equal to 1/4 pi epsilon naught Q over r squared, and then you have your r hat. Okay, so this one is the magnitude, and then you have here the your r hat as the direction of your vector. So again, this is just your E that is equal to 1/4 pi epsilon naught Q, magnitude of Q, r squared, is just the magnitude of the electric field of a point charge. Now these are some of the these are the vector fields showing the field of point charges. Again, for a positive test charge, all the electric field is flowing radially outward. So this is just a two-dimensional view, but again, all the electric field is flowing out radially outward. So you still have your electric field which are perpendicular here. Okay, so it goes radially outward from this field here. And on the opposite, for your negative test charge, you have electric fields that are flowing radially inward. Okay, so your positive test charge, you have radially outward radially outward electric field. Your negative test charge, you have radially inward. So radially around the radius um, of your charge. So radially. This is radially inward, and then this is radially outwards. Okay. In the same way, so previously you have your superposition of forces. So we also have your superposition of electric field, because of course it's not always the case that you only have one source point. You only have one charge on your source point. Of course, there are cases wherein you have many charges, which creates the electric field. Now, if you have, let's say, for example, a positive test charge and then a negative test charge, and you want to find for the electric field at point P here, okay, the total electric field at that point is just the vector sum. Again, that is just the vector sum of the fields due to all the charge present. That is, from here, you have your positive test charge. You know that the electric field for a positive test charge is radially outward. So you have this one here, a radially outward electric field along the direct line of action between these between the source charge and then the field point. So you have here radially outward electric field, and for a negative test charge, you know that this is radially inward. So the electric field goes directly towards your negative test charge. So you have here your electric field E1 for Q1, and then you have here your electric field E2 for your charge Q2. Now the sum of this one, the vector sum of this electric field, is the net electric field experience at this field point P here. Now, if you're going to do the vector sum from your let's say your parallelogram method, you draw parallel lines here, and then you also draw parallel lines here. Okay, so you know that this one here, this points towards your towards the net electric field experience. So let's draw it again. So we draw parallel lines parallel to your E2, and then you also draw parallel lines to your E1. So from this point here towards the opposite side, you have your net electric field, or the total electric field E at the point P experience at this point here. So this is the same concept with your superposition of forces. You have your vector sum of your fields. Okay, if there are more than one source points, and then you want to find for the electric field at some certain field point. Now, you have your electric field lines. So earlier you have seen that for your positive test charge, again, the electric field goes radially outward. So these lines here, these are what we call your electric field lines. Okay, and you can actually view this one. Okay, an electric field line is just an imaginary line or curve whose tangent at any point is the direction of the electric field at that point. Okay, so even though it's imaginary, you can actually view that one. Like say for example, you have here your grass seeds. Okay, just some ordinary grass seeds. Okay, and then you put these grass seeds on some like dish, and then on one end, let's say you put some wire here, an open wire, and let's say at this point here, this is positively charged, and then at this point here you have a negative charge of your wire. Okay, so these are with some separation distance, and these are not in direct contact, and then you'll see from your experiment that these grass seeds actually align to the electric field produced by these two wires here of opposite polarity. Now, as you can see here, you have these lines. You have this one here. Okay, not this one. You have these lines here. You'll see this one, right? So these are actually your electric field lines. Okay, And the electric field line is produced by two equal point charges. In here, we just have this one, the charges created from or outsourced from your wires. The pattern is formed by grass seeds floating on a liquid above two charged wires. And the electric field is tangent uh, and or sorry and the electric field whose tangent at any point is the direction of electric field at that field vector at that point. So let's say for example around here, this is your electric field line. So anywhere around it, around this electric field line, you have the direction of your electric field at that point. So if you want to find for the electric field at this point here, that is just tangent to this electric field line, those are your electric field points. These are some of the other electric field lines of point charges. You've already seen your positive test charge. So it's radially outward, as you can see here. If we have two charges, a positive and then a negative, or you call this one as a dipole. So this is a dipole. Okay. If you have a dipole, what you see is that again, from your positive, it is radially outward, and then for your negative, you have radially inward. So what happens if you have a positive and then a negative is that electric field flows from the positive towards your negative. So it's from positive to the negatives, as you can see here. If instead you have two like charges, two positive like charges, two positive charges. So since radially outward, and you know that like charges repel, you see why they repel from the electric field lines. It's here. You can see here that the electric field lines do not touch each other, so they repel each other. Here, your electric field, it flows from your positive to your negative. There are also other interesting electric field lines. Let's say, for example, you have a positive, two positive, and then one negative, and you'll see that your negative test charge actually moves around your two positive charge, depending on the orientation, of course, or depending on the initial position of your negative charge. Now let's solve some problems involving your electric field. Okay, first we go to, or we have an example on electric field of a point charge, and then after that one, let's discuss your electric field due to two or more source charges. So this is electric field vector of a point charge. Okay, so a point charge Q of magnitude -8 nanocoulombs is located at the origin. Find the electric field vector at the field point x equals 1.2 meters and y equals -1.6 meters. So in this problem here, you have a negative source charge, you have your Q, negative source charge Q, -8 nanocoulombs located at the origin. So here, you have this negative test charge here. Okay, again, this is a negative. Let me just erase this one. It's a negative test charge. And you're asked to find for the electric field vector at the field point, which is located at x equals 1.2 meters and y equals -1.6 meters. So it's on the fourth quadrant, and this is around here. So this is your field point. Now, since this is a negative test charge, you know that the electric field is radially inwards. Okay, so you have this line here, your electric field line, pointing radially inwards towards your negative test charge. So our answer, our electric field vector, should be pointing this way. So it should have, as you can see here, if you're going to just this one to get the components, okay, your electric field vector should have a positive y component and then a negative x component. So our answer should be something like that. Okay, so let's solve this one. Okay, so again, first are given are, you have your Q is equal to negative, you're given your Q negative 8.0 nanocoulombs, or we use the standard units. So this is 8 times 10 to the negative 9 coulombs. Okay, and that is at the origin. And the rest defined for electric field at this point here. So your electric field, the formula for electric field is you have your electric field E is equal to your K, which is your 1 over 4 pi epsilon naught, and then you have your Q, R squared, and then you have your vector R hat. You need this one, this R here. Again, the R is just the direct line joining your source point towards your field points. So you need this one here. You need this one here. This is your R. And just from your Pythagorean theorem, you form here a triangle. You can see you form here a triangle. This is 1.6, this is 1.2. So your Pythagorean theorem, you have your R is equal to 2 meters. Okay, so your R is equal to the square root of 1.6 squared plus 1.2 squared. So again, this is just from your Pythagorean theorem. Okay, so that is your R. Let me erase these things. Okay, so let's now find for your electric field. Let's get the magnitude first. So for your magnitude, you have your E is equal to your K, Q, R squared. This is equal to K, and then you have negative 8.0 times 10 to the negative 9 coulombs divided by 2 meters squared. So you have here your electric field, which is equal to negative 18 newtons per coulomb. Now you need to find for your vector R. So your vector R, or your R hat, your unit vector R hat, is just your vector R divided by the magnitude of R. So again, your unit vector points from your source point towards your field point. So this one here is your unit vector R hat. So looking at that one, that unit vector R hat, it has the vector R has magnitude, or sorry, let's just write that one. You have your xi hat plus your yj hat, okay, divided by your R. So your x is a positive 1.2 meters I hat, and then your y here, okay, as you can see, if you're going to decompose this one, you have a negative y. So you have minus 1.6 meters j hat. And this is over 2.0 meters. You'll see that your R hat vector is equal to, or your unit vector R hat is equal to, you have here 0.6 I hat and then minus 0.8 j hat. We multiply this one to your magnitude, negative 0.18. So you have this one, negative 18 newtons per coulomb times your R hat. So negative, or you have 0.6 I hat minus 0.8 j hat. Okay, so your vector field E, your vector electric field, is equal to, you have negative 10.8 newtons per coulomb I hat plus 14.4 newtons per coulomb j hat. I'm sorry for the messy solution, but you have this one here, your answer. So it has a negative x and a positive y. Let's see your electric field vector from here. Did we get it right? So again, this is your electric field vector. So you have a positive y, so this is checked, and then you also have a negative x, so that's checked. So you're able to see, or we're able to get the right direction of your electric field vector here. It's equal to your negative 10.8 newtons per coulomb I hat and then plus 14.4 newtons per coulomb J hat. So that is your electric field vector at point x equals 1.2 meters and y equals negative 1.6 meters. So let's have another example. This is the field of an electric dipole. So for an electric dipole, you have a positive charge and then a negative charge. Okay, so point charges Q1 of plus 12 nanocoulombs and Q2 of negative 12 nanocoulombs are 0.100 meters apart. Such pairs of point charges with equal magnitude and opposite sign are called your electric dipoles. Compute the electric field caused by Q1, the field caused by Q2, and the total field A at point B, and then C at point C. So you have here your electric dipole. Okay. You have here your positive test charge and then your negative test charge. These two are separated, or they are 0.100 meters apart. And you're asked to find for the electric field at point A, okay, which is here, and then electric field at point B, and then electric field at point C. You're going to compute electric field caused by Q1 alone at point A, and then at point B by Q1 alone, and then at point C by Q1 alone. And then you also do the same for your Q2. Okay. So again, you need to compute electric field caused by Q1 and the field caused by Q2 and then the total field. So you're asked of three. First is caused by Q1, then caused by Q2, and then the total field at your 3 points A, B, and C. So let's first write your givens to make it easier for us. So given. So you have your Q1, that is 12 nanocoulombs, or that is 12 times 10 to the negative 9 coulombs. Q2 is negative 12 times 10 to the negative 9 coulombs. Okay. You have from your Q1, again from Q1 to point A, that is your R1A. Let's call that one as your R1A. Okay, the distance from your Q1 to point A, so that is just 6 centimeters or 0.06 meters. And then your R2A meaning from your Q2 towards your point A, that is the distance from, so separation distance from Q2 to point A. So you have here 4 centimeters, or you have 0.04 meters. And then you have your R1B. So we're doing this one individually because we are asked of the field caused by Q1 on the by Q2 and then the total field. So your RB, so R1B from Q1 to point B, that is 4 centimeters or 0.04 meters. And then your R2B from point 2, okay, towards point B, that is 10 centimeters plus 4 centimeters. So you have 14 centimeters, or this is 0.14 meters. And then R1C, your R1C is 13 centimeters or 0.13 meters. And then your R2C from Q2 to point C, that is 0.13 meters. So these are your givens. So now let's solve for the problem. So first you're asked to find for the electric field caused by Q1 at point A, and then by Q2 at point A, and then the total electric field at point A. So for A, let us solve first at point A. okay, uh, by by Q1. So that is just your E1 on A, the electric field of 1 on A. So this is just your K times your Q over R squared. So your Q1 is 12 times 10 to the negative 9 coulombs divided by R1A, which is 0.06 meters, and then squared. And here at point A here, you know that this one is a positive test charge. So the electric field is radially outward. So you have here your E1A, which is along the x-axis. So you can now write here your R hat. Okay, your R hat is just your I hat. How did that happen? Because your R hat again is just your vector R over your magnitude of your R. So here from your source your field, this is your vector or your unit vector R hat. Your vector R is just 0.06 meters I hat, since that is just along the x, over the magnitude, which is 0.06 meters. So you're just left with your R hat that is equal to your I hat. So you have there your vector. You can solve that one. Your electric field caused by E1 on A. So that is equal to 3.0 times 10 to the 4 newtons per coulomb I hat. So you can verify that one using your calculators. Next, let's find for the electric field caused by Q2 on point A. So this is E1 or E2 on A. So you still have the same K, and then negative 12 times 10 to the negative 9 coulombs divided by 0.04 meters squared. And here, your R hat, okay, your R hat from your source towards your field, you have here, that's a negative x, so you have 0.04 meters negative I hat over 0.04 meters. So it's a negative I hat. So here you have negative I hat. Let me erase this one. And solving it using your calculators, so you get a positive answer. So you have 6.8 times 10 to the 4 Newton coulombs I hat. So it's a positive because you have here your negative 12 times 10 to the negative 9 coulombs times negative I hat. So you get a positive answer. So that means at point B, or at point A, here, the field caused by Q2, which is your E2A, is radially inwards towards your charge Q2, because that's a negative test charge. Now our last goal is to find for the total field. So the total field at A. So the total field of A is just from your superposition principle. So you have your EA, it's just your E1 on A plus your, this is equal to E1 on A plus your E2 on A. So that means your total field at point A is just 3.0 times 10 to the 4 Newton coulomb I hat plus 6.8 times 10 to the 4 Newton per column, and then I hat. So your total field at point A is equal to 9.8 times 10 to the 4 Newton per column I hat. So the direction is along the I hat, so the total field is this one here. So you were actually already given with the direction of your electric field. So if you were not able to get the right answer, if instead we got the negative, then from the diagram, we know it's already wrong. Okay, so that's your total field at point A. Okay, now so let's continue with the problem and let's solve for the field. The field caused by Q1 and Q2 on point B, at point B. Okay, so this time you're going to find the electric field at this point here, caused by Q1 and then caused by Q2 and then caused by the both source charges. Okay, so this is at point B. Okay, so let's first find the field caused by Q1. So you have your E1 on B. So this is your K times Q over R squared. So you have 12 times 10 to the negative 9 columns divided by, you have here your R. So you have 0.04 meters and then you square this one. And from here, it's just easy to see that your R hat, okay, which is equal to your vector R over R. You have your you have here your R hat. So your vector R is 0.04 meters negative I hat over 0.04 meters. So you have negative I hat. So this is times negative I hat. You can solve this one and you get a value of equal to negative 6.8 times 10 to the 4 Newton per column I hat. So we just take out the negative outside. So you have negative 6.8 times 10 to the 4 Newton per coulomb I hat. Now let's find the electric field caused by Q2. So this time this is E2 on B. So you still have KQ over R squared. So this is K times negative 12 times 10 to the negative 9 columns divided by, you have your 14 centimeters, or this is 0.01, 0.14 meters, and then you square this one. And here your vector R still points that way, and since still points that way, you still have your negative I hat. But just for you to know, okay, let's see if it's a negative I hat. So this is your R hat for your E2 on B. So your vector R is equal to 0.14 meters negative I hat divided by the magnitude 0.14 meters. So it's still a negative I hat. And you can solve this one. You get an answer of equal to 5.5, positive 5.5 times 10 to the 3 Newton per coulomb I hat. So these are the individual electric field caused by the two charges. Now let's find for the total electric field. Okay, so your E on B, it's just your E1 on B plus your E2 on B. Okay, so your E on B is just negative 6.8 times 10 to the 4th Newton per coulomb I hat plus 5.5 times 10 to the third power Newton per Coulomb I hat, you get an answer of EB, electric field point B, which is equal to negative 6.3 times 10 to the fourth power Newton per Coulomb I hat. So it's a negative. Okay. It's a negative electric field, or it points or is directed towards the negative x-axis, as you can also see here. So from the diagram, that's a negative electric field there, meaning at this point here experiences electric field that is towards the negative x-axis. Now for letter C, I will be giving it to you as an assignment here. At this point here, you're going to find for the electric field caused by charge 1, that is, you're going to find E1 on C, and then E2 on C, and then EC. So this is an assignment for you.